so I was a little surprised. The average is usually pretty much higher. Usually it's more close to 80 on that test. I'm a little surprised because that stuff is review. So this stuff is review too, and now you've got me nervous because it's review. So we go through it quickly because it is review. So just because it's review, maybe don't assume that you know it and spend just as much time studying it as you did for exam 3, which the average was higher than usual on. I'm confused. So exponential functions. Exponential functions are functions that show up a ton in calculus, and you can either have an exponential growth or an exponential decay. Exponential growth occurs when the base is greater than 1, and then exponential decay occurs when the base is between 0 and 1. So with an exponential function, the variable is in the exponent, and then the base is a constant. So a basic exponential function will always pass through 0, 1, and a basic exponential function will always have the x-axis as a horizontal asymptote. So for every basic exponential, by basic exponential we mean a constant raised to x. Constant raised to x, that's a basic exponential. All right. And so the base has to be greater than 0. Can't have negative base, because then all of a sudden you have negative numbers with funny exponents and you don't get a smooth curve. So we force the base to be bigger than 1, bigger than 0, and not equal to 1. Why do we not want the base to be 1? What would the graph of y equals 1 to the x look like? Yeah, just a line. And that doesn't have the sense of an exponential function. When we think of an exponential function, we're thinking of something growing quickly. And a constant function doesn't match what we're thinking of when we think of exponential function. So we don't let the base be 1. So it's exponential if the base is greater than 0 and not 1. Okay, so that's exponential growth, and it grows very quickly as you start moving to the right here. Now back here, when you're plugging in negatives, it's growing very, very, very slowly. It's not touching the x-axis, it's getting infinitesimally close. When we talk about exponential growth being fast, we're talking about over here. We move a little bit to the right and it jumps up a lot. Not over to the left. So let's look at some examples. Graphing these. Usually I recommend graphing 3 points for an exponential or 3 points for a log. And let me just go back for 1 second. There's 3, I didn't even slide down to my decay function. So there's 3 key points that I think are important to look at. And they kind of form this turn right there. That's the most important part of the graph. If it's an exponential growth, you know it's going to jump up and you know it's going to go towards the x-axis. But right in here is where we really need to focus. And those x values that I recommend picking are -1, 0, and 1. So what I recommend is doing a little table and always pick -1, 0, 1 if you're graphing a basic exponential. Got it? Yep. So it's decay when the base is between 0 and 1. So yeah, if I slide down here, we'll see that. Okay. So those are the 3 x's that I recommend picking, -1, 0, 1. That gives you sort of the turn. That gives you a good sense of what the graph is doing. So exponential decay, the base is between 0 and 1. Do you agree that that base is between 0 and 1? How could you rewrite that? If you have y equals 2 to the negative x, you might be saying, that's not a base between 0 and 1. What do you do with that minus sign? Or what can you do? Can't you treat this as 2 to the minus 1 to the x, so that's really 1/2 to the x. So there's 2 ways to look at exponential decay. You could formally have it like the definition states, that the base is between 0 and 1, or you can have an exponential decay where that fact is kind of hidden with a negative exponent. Okay, so with exponential decay, same thing. We're going to pick 3 x's. And if it's a basic exponential function, pick -1, 0, 1. Those always work. Those are great points to get you the turn of the graph right in there. And if it's exponential decay, you know it's going to infinitesimally approach the x-axis this way. And it's going to jump up fast if you're going to the left. Plug in -1 there, you get 2 to the 1, which is 2. So that's the point right there. -1, 2, 0, 1, always for a basic. And then 1, 1 half. So that's just y equals 2 to the x flipped through the y-axis. With that minus sign right there, you could say, oh, okay, that's a horizontal reflection through the y-axis. Right there. So you take 2 to the x and reflect it through the y-axis and you get that graph. That's our exponential decay. So let's look at a couple. And so we have, right away, before you even do anything, you know it's a basic exponential function, so you write down the x-axis as a horizontal asymptote. You know that right away. And then we do our little table, and -1, 0, 1. Always pick those. What's 4 to the -1? 1/4. 4 to the 0, 1, 4 to the 1, 4. This pattern should be very familiar to you already. If not, we'll pound it into your head, because graphing these basics you should be very fast at these by the final. So a little bit of practice to get back in the groove, but the pattern is really, really evident if you pay attention to those 3x values. We go to the next one over here, to 10 to the x. And again, we know it's an exponential growth because the base is greater than 1. So we know the x-axis is a horizontal asymptote. And we go to plot a few points. X and y, -1, 0, 1 again. And 10 to the -1. 10, 10 to the 0, 1, 10 to the 1, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see this pattern with these 3x values. The bigger the base, the larger the y value is at x equals 1. At x equals 1, the y value is exactly equal to the base. So if this y equals 10 to the x, we're up at 10 on 1. If it's 4 to the x, we're up at 4 on 1. If it's 20 to the x, we're at 20 on 1. And then on the left side at -1, it's always going to be 1 divided by the base. 1/10, 1/4. And really, it's kind of hard to distinguish there. The feature of this graph that really distinguishes it is this part right there. That point is where you really get a sense of how steep it is. The tails for them all, they would look about the same. The tail to the left. All right. Let's do these two. So y equals 3 to the -x. I think it's useful to rewrite that as 1/3 to the x. You don't have to. Do whatever you need to do to recognize that it's exponential decay. And we still pick the same x's, -1, 0, 1. 1/3 to the -1 is 3. 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. So when we go to graph this decay function, again, it's a basic exponential, so we know the x-axis is an asymptote right away. And we just plot those 3 points. So -1, 3, 0, 1, 1, 1/3. And that's our decay function. All right, you guys graph that one, 5 to the -x. To the -x. Decay away. thinking about exponential decay, is it clear that it decays very, very slowly when x is greater than 0? Right? It's really creeping towards that x-axis very slowly. Usually when someone says the growth is exponential, you think fast. And a lot of people aren't clear that if it's decay that's exponential, it's actually very slow.
I have a question.
Yeah.
Why is this
one? If you take a positive number and you raise it to the 0 power, that's always 1. So any non-zero number, not the 0. And generally in algebra classes, they'll convince you of that with a chart like this. They'll do something like this. Maybe I can't really think for a second. So 2 squared is 4. I guess they don't put x's and y's. Think about this for a second. 2 to the 1 is 2, 2 to the 0, 2 to the negative 1, 2 to the negative 2. So if you set up a chart like this, they just sort of, it's a pattern. We define it that way because it's got to match this pattern. As we ratchet our exponent down by 1 each time, what's happening over here is that we have consecutive divisions by 2 in this case. So if we want to continue with this pattern is what the rules come from. So we make the rules so that this pattern continues all the way down. So if you have a positive, any non-zero number raised to 0, you'll get 1. And most books will say that it's by definition, and it's by definition so that this pattern holds. Okay, so 5 to the negative x. Once again, if you want to rewrite that as 1/5 to the x, that's probably a better format if you want to really focus on the base game between 0 and 1. Doesn't matter though, you can plug and chug with either of those forms. Again, negative 1, 0, 1, all the time, and we get 5, 1, 1, 5. The x-axis is a horizontal asymptote, and we plot our 3 points. So negative 1, 5 is up there, 0, 1, 1, 1 there. Any other questions on that? Why we get what we get? All right. So, exponentials, this again is something you've seen before, but I want to emphasize some of the properties that come out. This number e, you see it all the time. They call it the natural exponential, the natural logarithmic function if you use base of e. The question is, well, where is this e coming from? And if we check out this quantity right here, 1 plus 1 over n to the n, it's that expression there should be familiar from the compound interest formula. Compound interest formula, you do 1 plus r over n to the nt, checking out the classes. So if we look at that, let's first consider, this is an exponential. We have a base, we have an exponent. Now, the base is not constant though, so this is a little different than what we think of as a traditional exponential. A traditional exponential, we have a constant raised to a power. Here, raised to a variable power. So here, let's just talk about what happens if you had 1.1 to the n. So if you had a base greater than 1, that's exponential growth. And what happens as n goes to infinity? If you take 1.1 and you start multiplying it by itself an infinite number of times, that goes to what? Where does that go as n goes to infinity? Where does that approach? What's that? Yeah. And that's exponential growth. Exponential growth. If that base is a constant greater than 1, it's zipping up. No matter what that is. That's going to go to infinity as n goes to infinity. Right, so as you go further out along the x-axis, it's going to jump up. And it doesn't matter how much tinier this is than 1. It's just a tiny bit greater than 1. Doesn't matter. It's going to infinity as n goes to infinity. Right? If you have a constant base greater than 1, it's going the y value is going to infinity, no matter what. If you have a constant base greater than 1. Okay. And what happens if you have a base less than 1? 0.9 to the end is going to go to 0 as n goes to infinity. And it doesn't matter how tiny, no matter how close to 1 this base is, it's still going to go to 0. If you take this number with a bunch of 9s and raise it to the nth power, it's still going to go to 0 as n goes to infinity. Doesn't matter. If you have a constant base and it's a tiny bit less than 1, as n goes to infinity, it's going to 0. Now when you take a number that's less than 1 and you multiply it by itself, it gets smaller. Now, a half times a half is a quarter. Take a number less than 1 and you multiply it by itself, it gets smaller. Take a number greater than 1 and multiply it by itself, it gets bigger. That's the basic principle that we're exploiting here. So now, when we look at this crazy expression here, this base is always greater than 1, but it's not a constant base. Right? That base is always bigger than 1 as n is getting larger and larger and larger. But the weird thing is that that base is getting closer and closer to 1. Right? And what happens, what's your hunch? When you look at that as n goes to infinity, your hunch is, most people's hunch is that it goes to infinity. Because the base is bigger than 1 for every value of n. And we know that 1.0000001 is going to go to infinity. So our hunch is that it goes to infinity. Most people would have that hunch. No one who's not familiar with math would ever say, oh, that goes to 2.71. You'd never guess that. You wouldn't guess that it goes to E. But that's what happens. So that's what happens here, though. If we take a look at a graph, we'll go to decimals for a second. And this, to show this is a little complicated. We have to do some, a little hard to show all the details. But if we look at a graph, we can see that it goes to E. And that's where E comes from. E is the limit. When you get into calculus, you call these things limits. And that is exactly where E comes from. And you can see it quite easily in the graph. Whoops, not dollar sign. Okay, so if we look over here, let's also graph y equals E. And you can see, as you go out further and further and further and further, blah, 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 it's going to get infinitesimally close to E. And that's where it comes from. So E is the so-called limit of this expression of x goes to infinity. Infinitesimally close to the number 2.71, blah, blah, blah. Okay. Now, to show that, we have to use logarithms. We haven't done that yet. But you've done logs before, so let's just go. Let's do it right now. So we're looking at this expression. We graph it and we say, oh, it looks like it actually has a horizontal asymptote, so let's assume it approaches a number. let's say that it approaches, let's assume that it's going to, I don't know how to do this cleanly though. Let's assume it approaches the number n. Then what you can do is take the natural log of those sides, and the n will pop down. You can do a little math. I don't want to do it actually. Just believe me, it goes to e. Goes to e. But you can do like natural log of both sides. Because we haven't done this concept called the limit yet. If we haven't done that concept called the limit, which will be in the very beginning of calculus, it takes a little while. So we'll just take it on face value. Take it from looking at the graph. All right. So how do we graph these exponentials if we have this base of e, this irrational number, e? And the graph is, of course, very similar to what we've been doing. So we do our chart, -1, 0, 1, plug that in, we get an e, we get 1 over e. So that's about a third. So at -1, we're at about a third. 0, 1, 1, e. E is 2.7-ish. Let's write it off there. So look at that. So that's the natural exponential, e to the x. And similarly, we have exponential decay with the base of e, base of 1 over e, I should say. We can write this as 1 over e. This is about a third to the x. Plug in your 3x values. Okay, so if we plug in -1, then we get e as our output. If we plug in 1, we get 1 over e. And graphs at -1 up at e, about 2.7, at 0 is at 1, at 1 it's about 1/3. So there's our natural decay function. And as we're going through and dealing with logs and things, it's really common to use the natural log. And in this class, it's hard to explain exactly why we prefer the natural log. When we're solving equations, it's very common that you have to take the natural log of both sides. And the argument can be made that you could take the log base 10 of both sides, because calculators all have base e and base 10 as their options. But when you get into calculus, you do this really fundamental thing called a derivative. And it turns out that when you're dealing with, and the derivative is just the rate of change, and it turns out that when you're finding a derivative, if you choose the natural exponential, the derivative is itself. It's the one function that has a rate of change that is itself, which is very interesting. So you're going to learn that in calc, and because of this nice property, and there's another derivative that's going to be important, is if you take the derivative of the natural log of x, that's got a base of e, you're going to get a very simple result there. You're going to get the derivative as 1 over x. If you use a base other than e for an exponential, it makes this process of the derivative more complicated. And the same is true with the logarithm. If you choose a log other than the natural logarithm, it makes this process of the derivative more complicated. These are pretty nice functions here. But if you change the base to something other than e, it's just messier. So in calculus, it's a little more obvious why our propensity is to use the natural logarithm function instead of a common log or another log, and to use the exponential with e instead of 2 or 4. Because in calculus, it just makes it easier. So we're going to see that we're going to use the ln function, the natural log function, quite a bit when we solve equations. Okay, transformations, old news. So let's identify our basic function first. Basic function here, y equals 2 to the x. So that's our basic function. Basic exponential is the basic function. And then we go to horizontal transformations first, and then vertical transformations. So remember that there's an order. Sometimes the order doesn't matter, but sometimes it does. So if you want to be careful, you always do it with horizontals first and then verticals. There's no verticals here. The only horizontal is shift which direction? Shift to the, yeah, so we shift right one unit. All right, so we just graph 2 to the x, and we're going to shift it to the right one unit. Not too complicated. And when we graph 2 to the x, we should get to the point where we can graph these without even writing the table, hopefully, for the basic functions. So there's 2 to the x. And then that's going to shift 1 unit to the right. So all these points here shift 1 unit to the right. And that's a picture of y equals 2 to the x. All right, you guys try to do that one, 32. 2 ways. So with these exponentials, if you don't like that negative exponent, which is a horizontal reflection, you can get rid of it here. You can bring that minus down and make that a 1/2 as the base. So you can take a 2 to the x as your basic function here, or a 1/2 to the x. Go ahead and do it. If you wanted, you could rewrite this as. Either way. Ignore the horizontal reflection by eliminating it, or you could go for it. That 5 out there, that's going to be a vertical shift, that's not a stretch. You know, it's kind of out in front and kind of looks like it's a stretcher. That's going to be a vertical shift, up 5. So if you have to, you could always rewrite this as minus 2 to the minus x plus 5. Which to me, that seems like a more natural way to write it, so that that vertical shift is at the end. It's the last thing that occurs. So I'm going to throw in the horizontal reflection here when I do it, just to mix it up a little bit. So I should identify the basic function that I'm going to use. So if we go this way, the basic function is going to be 2 to the x. If we went the other way, it would be 1/2 to the x. So basic function 2 to the x. Horizontal transformations happen inside the function, and inside for an exponential function means up in the exponent. That's in the exponential. So inside there, So we only have one transformation up there, that's a reflection. That's a horizontal reflection, so that means through the y-axis. And then our vertical transformation, left to right, reflection. And then there's no stretching because there's no multiplier right there. And then we have a shift up. So this reflection is through the y-axis up here, horizontal reflection, and this one is through the x-axis. And those don't necessarily cancel out. At least one person on the test said, oh, there's two reflections on one of the problems. And I was like, yeah, there's two reflections. And sometimes they do cancel out, but they do not always cancel out. So just because you see both of those there, don't just say, oh, I can just ignore those. Sometimes they'll cancel out, sometimes they don't. All right, so then we're going to apply our horizontal transformations first. And we're starting with a basic exponential of 2 to the x. So 2 to the x we know looks like this. Don't graph that as a line. It's not a line. It goes up very quickly. Okay, so first we're going to reflect through the y-axis, so that's going to take it this direction. So that is a picture of y equals 2 to the negative x. And now if you went over and did it this way, that's your basic function. That's 1/2 of the x. So that would be your basic function. I don't like that drawing. So one-to-one. And then next, we're going to reflect through the x-axis. The next picture, we're going to take that point there. It's going to come down here. That point's going to go down here. That point's going to go down here. And a reflection through the x-axis will create that. That's y equals negative 2 to the negative x. 2 reflections. So you can see that those didn't cancel each other out. All right, and then our last is to shift up 5 units. So up 5. 1, 2, 3, 4, 5. And so we up it over a little bit, and this way, and down 1. Okay, and now the graph shifted up 5. That means the asymptote also shifts up 5. So that asymptote, when we do a vertical shift, that asymptote comes along for the ride. So it's got to be up there at y equals 5. There's our final graph. It's the black curve. Any question on it? No?
I'm just trying to figure out how it reflected over the x-axis.
Over the x-axis, so down here?
Yeah, what are the second reflection?
So the second reflection is the one that's on the outside right there. So the first reflection is the inside one, which is the horizontal reflection, so that's through the y. And then that leading minus, the leading minus is a vertical reflection through the x. So that, so the green is simply the one inner reflection right there through the y-axis. And then when we throw the minus to the front, that is what's going to trigger the reflection through the x-axis. And then that 5 is on the outside. That 5 is not attached to the minus. It's not, a shift down to 5. That minus is a reflection because it's multiplied by the basic function. Any other questions on there? Okay. Carry on. Why don't you guys try that one? That has more than one horizontal transformation. And you dig it. That first one. And again, with these exponentials, there is some alternative ways to get at it, but try to do it with two horizontal transformations. So you can do it that way. There is some laws of exponents that you could use to rewrite that. But try to do it as it's presented. We have a break coming up. It's a great time to get caught up on sleep, on nap. Film final counts for a lot if you do well. Counts for a lot if you do bad. When you're thinking about those inner transformations, think trig. Think about what we did with trig. With trig, we had a lot of analysis on what was happening inside the function. And when we analyzed what was happening inside the function, we always wrote it in descending order. And what did we always do with that minus sign? What was the first thing we did with the transformed trig function when we looked inside? Factored. So this is what the form should look like so that you can do your transformations in the order that we've talked about. We always do reflect, stretch, shift, stretch or compress, and then shift. We always do that order, left to right. So if we rewrite it in descending order and factor out the minus, then we see our transformations in the correct order. Left to right, reflect, stretch or compress, and then shift. That's the form we should write in it. So that's just like we did in trig with the inside. Descending order, factor out the leading coefficient. So if we look at those horizontal transformations, what's the first one we see? A reflect. So once we write it in the proper form, it's just in order, left to right. And then is there a stretch or compression? No, because it's just a 1 in front. And then a shift, which direction? Opposite of what we see on the inside. Right? So just like with trig, it was always opposite of what we saw on the inside. We called it a phase shift back then. In trig, they called it phase shift. And on the outside, it's exactly what you see for a shift. So if it's a plus, if it's a minus 4 on the outside, we'd say it's down 4. But if it's a minus 4 on the inside, it's to the right 4. Okay, so shift right 4. And then there's no verticals. God, over there. All right, so we're going to go to our basic function first, 3 to the x. And we know that the horizontal asymptote is the x-axis. And we know over at 1, we're up at 3. 0, 1, and negative 1, 1/3. So there's our basic function, 3 to the x. Now we're going to do these in order. So horizontal transformation. reflect horizontally. That means through the y-axis. So our reflection, we're going to pull this point over there, push that point to the right. Something like that. That basically is y equals 3 to the negative x. And then, what do we do next? Just write 4 units. So let's add some, just write 4. 1, 2, 3, 4, 5. So that 4 units, 1, 2, 3, 4 right there. That point should be down there. And then to the left, 1 is up 2 units. So about right there. And that horizontal axis code still comes along. All right. Good. Exponential decay, which is what we would expect, because we have that leading minus, so we can think of that as 1/3 if we wanted to be x minus 4. All right, this one has a combination. Our basic function will be y equals e to the x. And then, what does that guy right there do? So it's a number, it's inside, so that's a horizontal thing, horizontal transformation, inside the exponent. It's a stretch compressed number. So which is it, a stretch or a compressed? So on the outside we would say it's a stretch, but on the inside we say it's a compression. So a number larger than 1 as a multiplier. Outside the function gives us a vertical stretch, but inside the function it gives us a horizontal compression. Okay. So horizontal transformation, the only one is compression by 2. Then the vertical transformation is up 1, shift up 1. All right, so our basic function, let's start with that. 1 comma e is right there, 0 comma 1, and negative 1 comma 1e. There's our basic function, So now we've got to deal with this compression thing. So, when you're doing a vertical stretch, everyone's pretty good at that. Most of you nailed those ones on the test. You multiply the y values by your stretch factor or your compression factor. When you're doing it horizontally, it's a little different. So, I've said that almost always a horizontal compression is the same as a vertical stretch. Okay? And if we were going to stretch this vertically, we would multiply the y value of that point and move it up. When we're doing a horizontal compression, it's the same essentially as a vertical stretch. Instead of moving the y values, we move the x value. So this x value right here is 1. And we divide that x value by our compression factor and get 1/2. So that point is going to move from 1 comma e to 1/2 comma e. And we can see that, oh yeah, that's effectively the same as a vertical stretch, because that's kind of stretching it vertically. And so the same thing over here. This is negative 1 comma 1 over e. We multiply, we divide by 2 and multiply by 1/2, and that's going to create the x value of negative 1/2 comma 1 over e. Now I know the horizontal stuff can be confusing. You can actually get around it here. You have y equals e to the 2x plus 1. Here's a way around it. You could say, oh, instead of using it with a horizontal, I'm going to treat this as e squared to the x plus 1. And then your base is bigger than 1. It's e squared. And you could get around doing that horizontal stuff if you wanted to. And this base is, whatever it is, e times v, 2.7 times 2.7. Whatever that turns out to be, 2.7. You could do that, too, to get around it. And here, this kind of, oh, no, we didn't finish. We still have to shift it. Do our shift. But that is a way to deal with the exponents so that you don't eliminate a horizontal transformation. And only have to go up 1. So up 1. That means the horizontal asymptote comes up 1. That shifts up. Let's do this one in green. We're going to go up 1 unit, so we should be just below that green tick mark. And that comes up 1 unit. That comes up 1 unit. So it's sort of that's our final one. Let me make another comment about this one over here also. So I said that you could change it around if you wanted. So if we have y equals 3 to the 4 minus x, so laws of exponents, you could rewrite this as y equals 3 to the 4 times 3 to the negative x. Everybody agree? Laws of exponents, when you multiply exponentials with the same base, you add the exponents. So this is doing that in reverse. So if you had those, everybody agree? Bases are the same, so you add the exponents. And then 3 to the 4th, that's 3 times 3, which is 9, and then 9 times 9 is 81. So 81, 3 to the negative x. And then if you wanted, you could get rid of that and make it 1/3 to the x. So you could say this is an exponential decay, 1/3 to the x, and then you vertically stretch it by a factor of 81. That would also be the same thing. All right, keep going, do an application. So this is interest rate one, and I'll put the formula up here that you should be familiar with in algebra. That formula, R is the rate, N is the number of compounding periods in 1 year, and P is the principal. So this tells us the amount if we invest P dollars at a rate of something compounded n times per year. Okay, so this says, suppose that $750 is invested at 7%, compounded semi-annually. So that means there's 2 compounding periods in a year. So we would, for part A, find the amount to which the investment grows to after T years. Okay, so the amount. And you can put the independent variable in there if you want. You don't have to. So that just says the amount after 2 years, AOT. That's going to be $750, so that's P. 1 plus R, the rate is 7%. So in the formula over here, we have to write that as 0.07. And then we divide by the number of compounding periods. And we raise that to the number of compounding periods times T. And if we want to simplify that a little bit, we can. So that's going to be 1.035. And that's an exponential growth. The base is bigger than 1, so the money's going up. you're investing your money, you want the base bigger than 1. Graph the function. I'm not going to do that. We plug it into Desmos. I'm not going to ask you to graph a crazy function by hand like that. But I would just plug it into Desmos. Let's do a couple of these for part C. So part C says find the amount of money in the account at these points. So, well, I guess actually if we do plot in Desmos, we could get all those very quickly. So let's just do it. I already have it open, so might as well throw it in there and take a look. So let's get rid of E, and then here let's use functional notation. And what was it? 750 times 1.035 to the x, or to the 2x actually. And let's go home. And let's see. All right, we're not seeing it there. Why can't I see it? If I plug in x equals 0, what's the y value? What's the y value if we plug in 0? 750, right? When you plug in x equals 0, that's corresponding to the day you walk into the bank with your $750. That base raised to the 0 is 1. 1 times 750 is 1. So it should be up at 750. So that y-intercept is way up there at 750. So if we keep zooming out, we'll see it. It's up there somewhere. Okay. So there's our graph. And so then it said find some things. So in Desmos, if I wanted to find f of 1, there it is, 803.42. If I wanted to find f of 5, it's right there. So one nice thing in Desmos is if you use functional notation, you can find your y values really fast by using functional notation. It's the whole point of functional notation. It's convenient. And was the big one f of 25? So f of 25, so 25 years later, you're going to have, $4188.70. So is there any question on that? So calculating those y values for the function, you're going to have to use a calculator because we're raising 1.035 to a number, so we're going to have to use technology. Everyone clear on if you were entering that into a scientific calculator, 1.035, and then you use your exponent key, you'd have to make sure your exponent's all wrapped up. That 2x has to be wrapped up. So 2 times whatever that is. Yeah. Okay. So I guess I should just grab maybe, oops. Let's grab a few of those values. Let's get our camera open. Get back there. Keep it going. Wow. That'll wake you up. All right, so there's some of the y values. All right, and then here's the hardest one. And this one is probably the most important. Part B. When will the amount of money in the account reach 3,000? So what we're trying to do is solve this equation for t. This is the most important one. We want to know exactly when it reaches $3,000. Obviously, we can do it with technology. We can come over here to a grapher, and we want to know when it's going to be 3,000. Let's just get rid of these things. So we could graph y equals 3,000, and then we could, go up to there where 3,000 is, and figure out where those two intersect. And it should tell us. I guess the way I have it zoomed in, we can't really see it here. But you could use the technology to figure it out. If you set your x interval so you could actually see where the two are intersecting, you could find that x value. on the TI calculators, you can figure out where the two curves intersect. The other way to do this, if you're going to use technology, you can subtract the 3,000 and then look for the x-intercept. That's probably the simpler way when you're dealing with any technology where two curves are intersecting, trying to find that point of intersection and zoom in so that you can see where they intersect. Sometimes most technology make that process a little difficult. So you could subtract, oops, did I hit delete? I guess I did. We could do it this way instead. We could do 750 times 1.035 raised to the 2x minus 3,000, and then we could look for the x-intercept. And we don't know where it is, but it's out there somewhere, and there it is, right there. So that tells us that it's going to take 20.149 years to get to 3,000. So using technology, that's how we would do it. But we need to use math. That's the key here for us. So if we want to solve for an exponent, we haven't talked about it yet today, but we're going to do it right this second. This will be our introduction. This is the whole point of a log. The whole point of a log is that a log allows us to solve for an exponent. That is the fundamental property that a log has that's beneficial, is that if you have some equation and you're trying to solve for the exponent, you can solve for an exponent using the log function. So here we would divide both sides by 750. We cancel out a 0 in the process, so we have 300 divided by 75 equals this. Okay, and so what do we do to both sides to get that exponent down to the main level? What do we do to both sides of the equation? Log. Yep, take the natural log of both sides. So we take the natural log of the left side. And here's where I was saying here earlier, you could take a common log, you could take log base, whatever you want. But the typical procedure is to use natural log because once you get into calculus, that function's so common and so easy to do calculus with. Now obviously we can reduce this to 300 divided by 75 is 4. So we're going to have natural log of 4 equals natural log of this side. And one of the log properties that we're going to be looking at today is that if you have log of an exponential, what happens with that exponent? You're going to remember it drops out in front as a multiplier. So what's going to come down is 2t, natural log of 1.035. Now we have what we want. We have a linear equation. The exponent of t is 1. And linear equations, simple, right? Once it's linear, all the constants go to one side. So here, we're just going to divide. So natural log of 4 divided by 2, natural log of 1.035. So that is the exact number of years. That is an exact answer. That's not an approximate answer. That is exact. And the approximation then, which is what Desmos was showing us, we type it into our calculator and find it, and we got 20.15 if we round to 2 decimal places. Here. So type that in, make sure you're getting that same answer. Should be. Can you combine these logs in any way here? And remember, if you have a log over a log, can you combine those? The answer is no. You can't combine those logs. So if you have a log divided by a log, you cannot combine it. If you have a log times a log, you can't combine it. If it was a log plus a log or a log minus a log, you can combine them. But multiplication or division of logs, you can't simplify. Now you could take that coefficient here and pop it up in here and square that 1.035. That's a possibility. You could actually take that 1/2 out in front and put it up as the exponent of 4 also and get the square root of 4 here too. That would be good. We don't need to. But somebody get 20.15? Yeah. All right, let's take a break. Take 10. Okay. Logs were created to deal with exponentials. Logs are inverses of exponentials. And we'll see that once we get to the graphing piece. Let's just go strictly from the definition of the log first, and then we'll go from there, and we'll get to the point where we identify the log as the inverse of the exponential. So here's how we're going to convert back and forth. So we use this definition to convert back and forth. And what we're going to say to ourselves is this. So if we're given a log expression, this log expression will equal the exponent on the base that gives the argument. There's this kind of circular thing. 3 raised to the other side needs to equal 9. So 3 raised to the 2 gives us 9. So that's how the definition of the log works. We have to understand how the base, the argument, and the constant all work together. So it's the base raised to the other side that gives the argument. So this next one, it's 2 raised to the what gives 64. So the 2 to the 6 gives 64. 2 to the 6 is 4 to the 3. 4 to the 3 is 4 times 4 times 4. That's 16 times 4, which is 64. Okay? This one. LOG with no base means there's a hidden base of 10. That's the common log. So if we have a common log, you don't have to put the base in there. It's understood that the base is 10. So this is the exponent on 10 that gives 100. 2. 10 to the 2 is 100. So we've got that spiral. Here, 8 to the what gives 2. 8 to the 1/3 gives 2. The cubed root of 8 is 2. 8 to the 1/3 is 2. So again, it's the base raised to the other side is equal to the argument. We always call whatever's inside a function, I call that the argument. I don't know why exactly, but that's what they call it. So 8 to the 1/3 is 2. How about this one? With ln, again, we see that there's no base there. ln of e. So e right there, the e we see, is the argument. And if you write ln, there's another, again, hidden base. That's the common law, the natural law. So there's a hidden base of e there. So now we're saying e to the what is e? E to the 1 is e. So that's an important property right there. We're going to see that a lot. If we take log base 2 of 2 to the 5, say, that's going to be 5. We're going to get this cancellation property. We have log base 4, 4 to the 3, we're going to get 3. So we'll have this cancellation property. If we have a log with a particular base of an exponential with that same base, we'll get that cancellation property. Okay, this one, 20. This says we have a hidden base of 10. So it's 10 to the what gives 1. And to the, not 10 times what gives 1, 10 raised to an exponent that gives 1. So that right-hand side is the exponent on the base that gives the argument. So it's 10 raised to the 0 gives 1. This one, again, there's a hidden base of 10. 10 to the what gives square root of 10. 10 to the 1/2 gives the square root of 10. Next one, 10 to the what gives 10 to the 8/5. 8/5. And there's that cancellation property. There's a hidden base of 10, and the cancellation property will give us exactly the exponent of the argument. 26 says, whoops. What the heck did I just do? I don't know what happened there. I delete that page though, we don't have that page. Okay, there we go. All right, 5 to the what gives 1. 5 to the 0 gives 1. 3 to the what gives 3 to the negative 2. Negative 2, there's the cancellation property again. Log base 2 of root 2. We say to ourselves, 2 to the what gives square root of 2. 2 to the half gives square root of 2. And then here, you can think of this as the cancellation property again because there's a hidden base of e, so we get negative 5. Or you can say e to the what gives e to the negative 5. Negative 5. All right, last one down here, 64 to the what gives 4. 64 to the 1/3. Let's check that out. So third root of 64. So that would mean 4 times 4 times 4 is 64. Yeah, 4 times 4 times 4 is 64. So that works. Third root of 64 is 4. All right, so that's how the definition of the log works. So the log is equal to the exponent on the base that gives the argument. You get this little spiral. 3 to the 2 is 9. 2 to the 6 is 64. 10 to the 2 is 100. 8 to the 1/3 is 2. E to the 1 is e. 10 to the 0 is 1. So get to that little spiral. Now, you can convert between bases and logs. And again, if you look at most calculators, there's only 2 bases. There's 10 and there's e. And that's because it's so easy to convert between bases that there's no need of putting a bunch of extra keys on there. Now, a lot of the newer calculators, you can actually type in different bases. But traditionally, the only bases that anyone would ever use were 10 and e, and still that's pretty common. Why use something different than 10 and e? So to change the base formula, you can change to any base you want. If you have log base 5, and this is how it's read, log base 5 of 8. Okay? So that's how you read that. The base log base 5 of 8. Log base 5 of 8. This is log base e of 8. Log base e of 5. And what we do is just split the base and the argument. Put the argument in the numerator, the base in the denominator, and then we can put whatever base here we want. So it's log 10 of 8, log 10 of 5. Log base 10 of 8, log base 10 of 5. Or we could take and make it natural log of 8 divided by natural log of 5. Or, if you wanted to be crazy, you could make it log base 11 of 8 over log base 11 of 5. It doesn't matter. You can switch to any base you want. In practice, this is the one that we most always will do. Okay, so just an example, we can change, we put the 19 in the top, the 3 in the bottom, and pick whatever base we want. And they all will give you the same exact ratio. Again, this one's the most common. You have to convert to a base, convert to natural log. All right. So let's get the graphing of these down, and here's where we're going to really see that logs are, in fact, inverses of exponentials. We'll graph these. And we're going to do something really similar to what we did with the exponentials. We're going to pick we're going to pick 3 x values, just like we did for the exponentials, but they're going to be slightly different. For the exponentials, we picked -101, right? Here we're going to pick almost the same things, except we have to do one modification. If I was going to plug something in for x, it would be really helpful if I plugged in something that could be simplified with this base of 2 here. So what I'm going to plug in so I can take advantage of the cancellation property is 2 to the negative 1, 2 to the 0, and 2 to the 1. So I'm going to take advantage of the fact that that base is 2. And I'm going to plug in powers of 2. In particular, 2 to the negative 1, 2 to the 0, 2 to the 1. And then what are the y values? What's log base 2 of 2 to the negative 1? Negative 1. Log base 2 of 2 to the 0? 0. Log base 2 of 2 to the 1? 1. Now when we go to plot these points, we want to rewrite these so that we can find these x values a little more cleanly. That's 1/2, 2 to the 0 is 1, 2 to the 1 is 2. So we're going to plot those 3 points. And with a log function, the y-axis, a basic log function, not transformed, a basic log will have the y-axis as a vertical asymptote. And then we plot our points. So we're going to have 1/2 comma negative 1, 1 comma 0, and 2 comma 1. So there's our log function. Right there, basic log. And so logarithms, if the base is greater than 1, they're growing. There's a lot of folks that will think of exponentials as growing and logs as not growing. But logs grow. So that's a growth function, but it's slow. It's very, very slow. It is going to creep up super, super slow. And the larger the base is, the slower it's going to grow. So if we look at log base 5, we're going to pick 5 to the negative 1, 5 to the 0, 5 to the 1. So the y values will be what we think they're going to be. And then let's rewrite these x values so that they're easier to plot. We'll write these x values as 1/5, 1 and 5. So 1/5 comma negative 1. Oh, 1 comma 0 again. And then 5 comma 1. So as we increase the base, it's just going to grow that much slower. We have to go that much farther down the x-axis before we get up to 1 unit. So log base 10, we have to go over to 10 before we're up at 1 unit. Log base 15, we have to go out to 15 before we're up at 1 unit. The log functions grow very, very slowly, but they're growth functions if the base is bigger than 1. All right. Any questions on plotting those?
Are you getting the y value?
So we're finding the y values by simplifying. So we're plugging in the x value of 2 to the negative 1. When we plug that x value of 2 to the negative 1 in here, log base 2 of 2 to the negative 1 is negative 1.
Oh.
So the y values are negative 1, 0, 1. So with exponentials, the x values were all negative 1, 0, 1 that we used. For logs, it's the y values that are going to be negative 1, 0, 1. For basics. They're not transforming. All right, let's try this. So now the base is 1/2 here, so it's less than 1. Let's see what happens. So we're going to pick our 3 points. We want to take advantage of the cancellation property. So we're going to pick 1/2 to the negative 1. We're going to pick 1/2 to the 0. We're going to pick 1/2 to the 1. And what is log base half of half to the negative 1? Negative 1. All right, so let's convert these x values over here into easily plottable numbers. 1/2 to the negative 1 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. So those are our 3 x values that we're going to use to plot this log. And we're going to notice that this is not, it's not quite the same as the last one because that base is less than 1. So we're going to get 2, negative 1, still 1, 0. So on the exponentials, it's 0, 1. That's on all the basic exponentials. And on the basic logs, it's 1, 0. And then 1/2, 1. Okay. So very similar to exponentials. If the base is greater than 1, we have growth. So if we have a log base greater than 1, still growth, it's just super slow. And in both cases, if we had a base that was between 0 and 1, a fractional base, both were decaying. So that's a logarithmic decay right there. Now let's graph the natural log of x. So we're going to pick, again, x's and y's. The base here is e, so we're going to pick e to the negative 1, e to the 0, e to the 1. And then what are the y values going to be? Negative 1 and 1. Yep. If we convert these over to more easily plottable x values, we have 1 over e is about a third, 1, and then e. Plot that. So here, where we know that we're going to have logarithmic growth. We're going to have growth because the base is bigger than 1. The base is e. Anytime the base is bigger than 1, whether it's for a log or an exponential, there's growth. We know we're going to have growth. All right, so first number is about 1/3, negative 1. Second number, 1, 0, second order pair. And then the third order pair, e, 1. So about 2.7, 1. So logarithmic growth, very slow. We're up at a y value of 1 when we reach e on the x-axis. All right. Any questions on the graphs? Now it's your second time going through the basic graphs. Hopefully you can zip them out pretty quickly. So the key is getting those 3 points. You get those 3 points right at the turn, you're good to go. All right. So now we're going to analyze this whole inverse piece. So let's take a look here. So if we have the function a to the x, a growth function, an exponential growth, it's going to look like that. The inverse of it, geometrically, is the reflection through the line y equals x. That's how you graphically think of two functions that are inverses. They're reflections through the line y equals x. So y equals a to the x, or let's use that easier function notation. F of x equals a to the x. That's that one, and the inverse function is log base a of x. So if we have f of x equals 2 to the x, what's f inverse of x? Log base 2 of x. Those are inverses of each other. If we have f of x equals 5 to the x, what's its inverse? Log is 5 of x. Yep. So those are for the growths. Exponential growth, logarithmic growth. For the decays, if we have a to the x with a decay function, so a is between 0 and 1, then its inverse is same thing. Just take the log with the same base. That'll be the curve that corresponds to the reflection through y equals x. So this is note there, note that the graphs of f and f inverse are reflections across y and y equals x. That's a property of inverses that we've seen in algebra. So in the simplest sense, an inverse is found by reversing the x's and the y's. So that's what we've done. We'll do another thing first. So if I want to just take a look for one moment, we'll do one little development thing. Let's look at a very specific exponential. Let's look at 3 to the x. So that function right there is f of x equals 3 to the x. So let's just go through the process that you would have done in algebra. In algebra, if you were told to find the inverse, you would convert to an xy equation first. You would convert from functional notation to xy notation. So you would say that y is equal to 3 to the x. And then what was the next step if you wanted to convert and find the inverse function? What did you do after you went to xy notation? You switch the variables, right? Because that's what an inverse is. Inverse is just the ordered pairs reversed. So we would switch the x's and the y's, and then solve for y. That's the inverse function. That's what you did in algebra. So now to solve for y, we now know how to do that. We could take the natural log of both sides, but if we want to be a little bit more in line with what they just demonstrated, if we take the log base 3 of both sides, then we're going to be able to take exact advantage of the cancellation property. That cancels to just y. And then the last step was to convert back to functional notation. So this told us that f inverse is this, log base 3 of x. So this shows us that if f is 3 to the x, f inverse is log base 3 of x. So those are inverses. And then let's just explore the property that you looked at a lot with inverses in algebra. If you do a composition, if you take the inverse function and put it into the function, what are you supposed to get? You remember? F and f inverse undo each other. So you should get just x. That's one of the properties of inverses, is that they undo each other. So if you put f inverse into x, you get x. If you put f into f inverse, you get x. Let's check. So f inverse into f. So we're going to do f inverse into f. So we're going to do 3 to the log base 3 of x. And there's an exponential cancellation property that we haven't looked at yet, but will show up. This will be a cancellation property for exponentials. That will turn into just x. And then the other property is that if we throw f into f inverse, so now we're going to put that into that, we get log base 3 of 3 of the x, and that's just x. So it's a property of inverses, that you plug them into each other, you get x. So let's question on principle of inverses. Undo each other. Let's do one of these guys. Forgetting. This might be important. So students in a computer science class took a final exam and then took equivalent forms of the exam at monthly intervals thereafter. Who wants to sign up for that study? So you take the final exam and then you keep taking it months on down the line. The average score as a percent after T months was found to be given by this logarithmic function. What was the average score when the students initially took the test? Or what is the average score in the beginning? So in the beginning, that's when time is 0. You take the test. And what do we get there? So S of 0 is, what's that? 78. That's the initial score. Because log of 1 is 0. We've just seen that log of 1 is 0 for any base. Right? All basic logarithmic functions pass through the point 1, 0. In other words, log of 1 is 0. All right, so that's the initial average. What was the average after 4 months? Okay, so to figure it out after 4 months, S of 4 is found by plugging in 4. So we're going to have 78 minus 15 times log, common log, of 5. So we're going to do, somebody type that in your calculator, 78 minus 15 log 5, and we'll round to the nearest integer. 78 minus 15 log 5. Common log of 5. 67.5, so I round to 68. 68. All right, so after 4 months, that's what happens. After 2 years, which is 24 months, let's see what happens. That's going to be 78 minus 15 times the common log of 24 plus 1 is 25. So type that into your calculator. 57. All right. Graph the function. We can graph this in decimals. Let's not bother doing that. So then the important question, after what time was the average score 50%? So here we're trying to solve this equation. So for D, we're saying we want the answer to be 50. Let's figure out when that occurs. How many months later? So we've got to solve that equation for T. So solving a log equation, just like any equation with a variable, you've got to unravel it. So let's get the numbers that are added or subtracted out of the way. So we subtract the 78. We get minus 28 equals minus 15. Common log equals 1. Divide by minus 15. We're going to have 28 over 15 equals the common log equals 1. All right, so now we have a log equation. The t is on the inside. Log equations and exponentials are two sides of the same coin. Anytime you have a log equation, you can flip the coin and turn it to an exponential. Anytime you have an exponential, you can flip the coin and turn it to a log. So that's what we're going to do here. We're going to convert this back to an exponential, or convert it to an exponential. Very frequently, if you have a log equation, you convert to an exponential, and if you have an exponential, you convert to a log. Very common. So the base on this is 10. So we're going to say that the inside is equal to the base raised to the other side. So 10 raised to the 28 15ths. Then we subtract 1. And this would be our exact number of months that it would take. That many months. Now, the problem like this in application, they typically don't want an exact answer. They typically want an approximate answer because that's more revealing. So if somebody type that into the calculator to get our approximate answer. This is exact. Here's where the misconception happens. When you look at that, it doesn't feel very exact. So exact answers, there's no approximation. It's approximate answers that are actually how we go through our life, approximating all the time. The approximate answer that's going to look more, the approximate answer in a lot of ways looks more exact, but it's not. Okay, what do we get there? 10 to the 28 15th minus 1. 73 months. Is that a combination? Did you subtract 1? Did you get 73?
Yeah.
Okay. So 73 months. 73 months. So whatever number of years that is, divide that by 12, you get the number of years. So 5, 6 years is 72 months, so just over 6 years. So that's interesting, right? Because it looks like it declines pretty quickly at first. You know, it goes from 78 to 68 to 57, but then it really slows down after that. All right. Next. So let's explore some of these properties a little more carefully. These are the three main properties of logarithms. Product, quotient, power rule. And when you get into calculus, you're going to have product, quotient, and power rules for derivatives and integrals and all sorts of other things. Mostly derivatives, actually. Product, quotient, power rules. So let's understand the product, quotient, and power rule for logs. Log of a product turns into a sum of logs. Log of a quotient turns into a difference of logs. And the log of a power, the log of an exponential with exponent, the p drops out in front of the multiplier. Those are the three properties. And here are a couple of examples. We can take log base 3 of 18 and we can separate it into log base 3 of 6 and plus log base 3 of 3. We could also use 9 and 2, right? You could make this log base 3 of 9 plus log base 3 of 2. That would work. With log base 3 of 9. What exponent on 3 is 9? 2. So you could do that. That's simple. That can be simplified. The other piece doesn't. That looks a little bit like an exponent. It's not supposed to be an exponent. Log base 3 of 2. For the quotient, log base 2 of this, we take the numerator, subtract out the denominator, power, drop that number. So those are the three basic rules. The biggest mistake that I see with rules is that if you have, say, natural log of 2 multiplied by natural log of 3, or natural log of 2 divided by natural log of 3, there's nothing to do here. You can't, there's no simplification there. So it's when you're adding or subtracting logs that you can use a log property. But if you're multiplying or dividing them, there's nothing. This is already reduced. That's already reduced. So you can't do anything there. Okay, so if you're multiplying or dividing them, done. The only thing you could do is type it into your calculator and get an approximation. There's no algebraic maneuvering here. So let's practice a few. I'll do 4, I guess. So in 4 it says express as a sum of logs. So this would be log base 4 of 64 plus log base 4 of 4. And now it just says express as a sum of logs. That we could actually reduce if we wanted. Let's do it just because it's good practice. What is log base 4 of 64? 3. Because 4 to the 3 is 64. And what's log base 4 of 4? 1. All right, you guys do 5? Write it as a sum of logs. Log base t of 3y. So writing it as a sum of logs is simply log base t of 8 plus log base t of y. Any questions? Pretty straightforward. A little more practice of these. As a product, here we're using the power rule. So if we have a power on the inside, that's going to come out in front as a multiplier. And similarly for 14, that negative 8 comes out as a multiplier. And when we have division on the inside, it turns into subtraction. So this is going to be log base A of 76 minus log base A of 13. And this will be natural log of A minus natural log of B. Those are our three main properties: product, quotient, and power. All right, you guys try this. 36. So write it as a single logarithm, and if possible, simplify it. What's that? Did I? Oh, thanks, Sarah. Oh, I did! Oh, great. I did skip a page. Thank you. Sorry. Let's finish that one off first, then we'll go back a page. I don't know how I did that. I touch it the wrong way. It jumps. So do 36, then I'll jump back and do the other page. So write it as a single logarithm and simplify if you can. So our product rule says that that's going to equal log base 10, or common log, you just say log, of what? We multiply those two. So log of 10, log base 10 of 10, and what does that reduce to? 1. Let's go back to that page that someone skipped. So express in terms of sums and differences of logs. I'll do the first one, you guys can try the second one. So here what I'll do first is separate this into log base b of the numerator minus log base b of the denominator. And then in the first log expression, we can separate that with the product rule. So that's going to be log base b of x squared plus log base b of y. And then over here, we can bring that 3 down in front, 3 log base b of b. Then we're going to simplify this. The power of 2 can jump in front, so we have 2 log base b of x plus log base b of y minus 3. Cancellation property. Look good? You guys do 30. So the basic idea here is that we want to eliminate division, multiplication, and powers on the inside of the log. We want to turn it into a sum and differences of basic logs, multiples of basic logs. step 1, what's the exponent on the entire inside? 1/3. Right, because that third root, that's the predominant operation first that we have to reduce. So that's going to be 1/3 natural log of 5x to the 5th. And here's where we have to be careful. Here is a very common mistake here, and that is to bring the 5 out in front. Right now, when we look to the inside, to the argument of this log, the predominant operation is multiplication. That power is secondary. Right? The first thing that's happening in there is we've got that multiplication. So we're going to have to parse this up into 1/3 times natural log of 5 plus natural log of x to the 5th. Now we see that we can reduce that second term over there. So it's going to end up being 5/3 natural log of x. So we just have to be careful that we ratchet our way out step by step. All right, try this one, 32. Log base C. Sure. It isn't 5 there, but it is 1/3 in front that has to be distributed. So if you left your parentheses, then yeah, there would just be a 5. If you leave your parentheses, then it stays with this. Yeah.
Oh,
Outside of each. So this one, similar to the last one, there's a predominant operation here of a 1/3 power, so that 1/3 comes out in front. We're going to log base C of this fraction. Now when we look inside that fraction, the predominant operation is division. So we can break it apart with division. Break the division apart into subtraction, I should say. So we get that. Predominant operation in the first log we see there is multiplication. That's the next step. We'll leave that 1/3 out in front for now. So we're going to log base C of y to the 3 plus log base C of z squared minus predominant operation. There is the power, so we can bring that down. That. And then we'll pull down the power on the first two and push the 1/3 across. So 3 comes down, multiplies by the 1/3, and becomes just a 1. So here we have log base C of y. For the second one, the 2 comes down, we distribute the 1/3, so we have 2/3. Log base C of z. And then the third term, distribute the 1/3, and we'll get 4/3 log base C of x. Happy campers? All right. Let's go to this one that we started. 38, this is going to become natural log of 54 divided by 6. So we can reduce that a little bit. 3 goes into both. Oh, will be 9 times 6 is 54, so natural log of 9. Can't go any further though. So this one, if we want to combine it, before we can do the division, the difference of logs will turn into division, but we have to get those coefficients out of the way first. So for these ones, we're going to have to rewrite this as log base A of x to the 2/5 minus log base A of y to the 1/3. Then we can apply the quotient rule. Once we have those coefficients jacked up into the exponent position. And that would be our final answer. The last one. Common log of x cubed minus 8 over x minus 2. Can we simplify that? People remember the difference of cubes? Say that again, same opposite. Same opposite, always positive. That difference of cubes? I don't remember that expression. Let's see if I can figure it out though. So a cubed minus b cubed. You erase the exponent on the a and the b first. That always goes in. And then the second factor, it looks almost like a perfect square trinomial. If it was a perfect square trinomial, there's two forms of a perfect square trinomial. Perfect square trinomial can be a squared plus 2ab plus b squared or minus 2ab. The middle. And the only difference here for a difference of cubes or sum of cubes is that you have to erase the 2's. And so we get a squared, and the signs are always opposite. So we get that. And now, Kelly, what was your expression again?
Same, opposite, always
Same, opposite, always positive. Okay. So same, opposite, always positive. So difference of cubes gives us that. Now, of course, here, if you weren't sure, if you thought, oh, yeah, I know that's a difference of cubes, that might go into it. Of course, you could do long division or synthetic division. And it would all come out in the wash. So this will reduce the common log of x squared. So let's just come over here and write the x cubed minus 8 out. We're going to think of that as x to the 3 minus 2 to the 3. So it's going to be x minus 2 multiplied by x squared. And what's the middle term going to be? What would that middle term be if we use that pattern? Plus AB. This is acting like A. This is acting like B. The minus is not part of B. B is just that. So we're just going to multiply A times B, and A times B is 2x. And then last, 4. B squared, and B is 2, so we get 4. So that tells us that we're left with x squared plus 2x plus 4 in parentheses. It's all there. And again, if you didn't remember difference of cubes, long division, synthetic division will absolutely work just fine. Just fine. So just for completeness, if we had a sum of cubes, we erase the 3's, and then look at that. Same, opposite, always positive. advance one side. All right. You do the first one, you guys do the second one. So here, opposite, we're just going to combine it into a single log. So to do that, the first thing I'm going to do is see this 2/3 is way out in front. I'm going to distribute that, and then it will be coefficient. There will be a coefficient, and so then it can come up as a power. So we're going to write this as natural log of x squared minus 9 to the 2/3 minus natural log of x plus 3 to the... Oh, I see some simplification we could get rid of first, actually. Let's do that. Let me go back up. Now I'm noticing, do you see that you can combine those first two terms and get a simplification in there? We write that as x squared minus 9 over x plus 3. Doesn't that simplify? Right? X minus x, the numerator becomes x minus 3 and x plus 3. So let's do that. That simplifies it. So then we're going to have natural log of x minus 3. Then we'll pull up the 2/3. And now we can combine that with the product rule. So that will give us natural log of x plus y times x minus 3 to the 2/3. That's one log. Most people don't put extra brackets in here, but you just have to be careful if you're typing something into your calculator. If you wanted to type something in your calculator like natural log of 2 times 3, if you want this to be natural log of 6, make sure you wrap that up there and put that 6 all in parentheses. All right, you guys do this one. So write that as a single log. When you look inside that big set of parentheses, we see addition and subtraction. Coefficients are all 1, so we're good. We don't have to deal with any exponents jumping up yet. So what we can do here then is turn this into multiplication of these two. So we're going to have the fifth root of that. Let's write it as x to the 3/5 multiplied by y to the 2/3, and then divided by 16z to the 5th in parentheses to the 1/4. So we can combine all those quickly, one fell swoop. And then that 120 is going to become an exponent on all of that. And down here, let's simplify this. The fourth root of 16 is 2. Z to the 5/4. That's going to all be 1/20th. And then we have to distribute that 1/20th power to each. So we're going to end up with x to the, let's see, 5 goes into 120 how many times? 24 times? And then 24 times 3, 17. And y. 3 goes into 124, 4 times 2 is 80. And down below, we have 2 to the 120. Let's just leave that line. And then z, 4 goes into there 30 times, so z is 150. Of your single log. Next slide. Okay, so here they give us some information, and they want us to use that information to rewrite these. So they tell us all that stuff up there. Log base A of 7 is 0.85. Let's see if we can use subtraction here. So we would write this as log base A of 1 minus log base A of 7. What's log base A of 1? 0. And then minus log base A of 7, they give us that as 0.845. So we end up with negative 0.845. This one over here, nothing special here. They give us both of these. They tell us that the value for log base A of 2 is 0.301, and the value for log base A of 7 is 0.845. So somebody type that into your calculator and give me 3 decimal points for that. So 0.301 divided by 0.845. 0.356. Thank you. And then they do the same type of thing for this other one as well. So we're going to try to rewrite this so that we can use the information that's given. We're going to rewrite this as log base b of 5 minus log base b of 3. They tell us log base b of 5 is 1.609. They tell us log base b of 3 is 1.099. We subtract those two, and what do we get? Say again? 0.51, thanks. How about this one? Is there a way we can rewrite that and get at it? So we have the 5 and we have the 3. Can we somehow separate that? What if we write this as log base b of 3 times 5 times b? That would be log base b of 3 plus log base b of 5 plus log base b of b. And what's log base b of b? 1. So then we're going to have log base b of 3, which is 1.099. Log base b of 5, which is 1.609. Somebody get that entered and equal. What do we get for that? That. So, 3 basic properties of logs. Play around with those. I think we have just one more slide. This one. Right, so let's get to this one. So we have our 3 basic properties, then we have those cancellation properties. And this cancellation property here is when the log is in the exponent position. So the first cancellation property we saw, if we had something like log base 5 of 5 to the x minus 2, we would get x minus 2. So that first cancellation property. Our second cancellation property, and there's an example of the first cancellation property. Here's our second cancellation property. If the log is up in the exponent position. So here, cancellation property, get the 5. Here, cancellation property, and we're going to get 4x minus 3. So if we come down for these guys, what's this first one going to equal? Cancellation property, that's the old cancellation property. We get 2713. I think it's so far away. And how about the cancellation property here? Not 3, x to the 3. We have to get that whole argument of the log that's up there. So these guys cancel. And then how about this one? So here we're going to end up with, yeah, let's rewrite this just to see it clearly. So that's b to the 3 halves, so we end up with 3 over 2. All right, let's stop. Week 13, coming to a screaming finish, one more day. Then we get a break. Wow.